Okay, this is recording number 2. I'm using the webcam, make it a little bit more personal this time. So I want to talk about with this presentation. This is the alkali metals and earths. Basically, I'm going to start talking about the ceramic oxides, their properties, and their parent materials. Okay. This is a page. I'm always going to have the periodic table of elements available for you. It's actually a pretty useful tool. So the periodic table is going to be in every one of these more technical presentations. Okay, alkali metals. These are fluxes. As we learned from the previous presentation, fluxes are something that helps silica melt or lowers the melting temperature of silica. And so the alkali metals, as you can see, in this row right here, we're going to be dealing with sodium and potassium mainly, okay? And there are a number of different sources for these materials. And typically, sorry about that, my Mac mouse, it will do that with these presentations. Okay. There are, basically, I'm just going to talk about specific materials, namely the materials that we keep in our studio, and the different characteristics of these. Now, the alkali metals typically make clear glazes. They don't opacify in any way. They don't crystallize. They actually have really high expansion rates, which means that they crack. And they're typically pretty soft. However, these metals are really, really active fluxes over a really wide range of temperatures. So they're really important to have in pretty much every glaze that you make. They also have really high color responses. There's the saturation levels of color in these glazes are usually really high. Excuse me. Okay, the first one is potassium oxide. You can see right here, K2O, all right? And, excuse me, this material is very similar to sodium. And in fact, you will find these very interchangeable. Excuse me. And typically, you'll find this in what's referred to as a potash feldspar. So whenever it's a feldspar that's potassium-based, we're going to refer to that as a potassium feldspar. You can find those materials in our studio. There'll be Custer feldspar, Cornwall stone, and pearl ash, which is a more it's not a feldspar. It's more of a material. It's a potassium carbonate, but it's soluble, and I don't use it. So I would just stick to adding potassium into your glaze mixtures by using Custer feldspar is always a great source. That's an American feldspar out of the Dakotas. Okay, you can see right here, this is a potassium-based glaze. This is a reduction glaze, cone 10. It's referred to as a temaku. It's a traditional Japanese glaze. It's usually very simple. You can see right here, this one has, what's that, 6 ingredients. A lot of times temakus will be anywhere between 4 and 5 ingredients, but the inclusion of zinc for some reason, at a really, really low percentage, I might add as well. Anyways, you can see right here that the Custer feldspar is 48% of the glaze, meaning, you know, the majority of the fluxing material is going to be potassium. You can see over here, this image, this is going to give you what Custer feldspar as a material and how it melts. Actually, I'm sorry, right here, it's Kingman feldspar. That's referred to as G200, which we do have in the studio. I apologize. It's been a while since I've seen this presentation. So anyways, right here, you can see the chemical formula right down here. The K2O is at 0.73 compared to 0.25 and 0.01 calcium, and that's 0.25 sodium. And that's reference to silica at 6 molecules. So you can see it's an overwhelming amount of potassium in the feldspar, which makes it kind of the leading fluxing ingredient. You can see over here, I believe this is cone 06, this is cone 6, and then this is cone 10. And you can see how these melt. Hold on a second. Let me see if I... Okay, sorry about that. Let's get back into this screen here. Okay, very good. I wanted to reference the book that I got these little test tiles from right here. It's actually cone 04, cone 5, and then cone 10. You can find that in the Craft and Art of Clay book. There's all of these melting swatches right here. So that's on page 166. That's a really great reference if you're thinking about choosing different materials. All right, let's move on. The next one is lithium oxide, lithia. This particular material is really good for mid-range glazes. It's typically used for like cone 4 to 6 to 7 glazes. You can use it in top firing temperatures. It's a really active flux, especially in those mid-range temperatures. So I don't use it a whole lot in cone 10 glazes. You can, I would probably use it sparingly. But anyways, you can find lithium, most of the time it's used in spodumene. Spodumene is a really consistent source of lithium. Okay, let's see if we have some lithium-based materials. Okay, here we go. Lithium feldspar, lithospar. You can see right here, this is a molecular formula we refer to as the unity formula. There is a presentation about that. But I can just get into it real quick. You can see these are all of the materials that are in the feldspar, okay? And so you're going to have some sort of alkali along with alumina and silica, okay? Silicon dioxide, actually. You can see these numbers right here. These are all in reference to molecules in relationship to all of the fluxes equaling 1. So if you can see right here, lithium is 0.4, potassium is 0.2, that equals 6, and then plus 0.4, that is in ratio to 1. So when we're talking unity formula, that means all of these fluxing materials in their chemical analysis are equal to 1. And then that will help us understand the ratios of alumina and silica in relationship to all of these materials. Anyways, that's maybe that'll make sense. I'll focus more on that in a later presentation. But anyways, it might help you understand these types of equations here, or these chemical analysis better. Okay, so anyways, what I'm getting at right now is that 0.4 lithium, that's a pretty strong source of lithium. Spodumene right here, down here, lithium compound, that's Li2, Al2O3, and 4 silica. So that's in ratio, that's a lot of lithium as compared to any other material, and alumina and silica. The strongest source of lithium is lithium carbonate. I don't use it very often. I don't know a whole lot about it. So, you know, use at your own risk. It looks like over here, these test tiles, it appears to be spodumene right here, and you can see it melts pretty well at cone 5 and 10. You can see too that because of the inclusion of silica and alumina, that it's more of like what you would expect a complete glazed surface to be. This, I believe, is lithium carbonate, I'd imagine. Let me double check. Hold on. Okay, sorry about that. I just wanted to double check these tiles here from my book. Again, I made this uh, presentation about a year ago. So, anyways, okay, so right here, this is the spodumene tile right here. You can see at cone 10, it's really, really active in flux. This is the lithium, the lithospar. And again, with its relationship of alumina and silica, it changes the overall characteristic. I was right, this is lithium carbonate. I would expect this to be just like a really hardcore glassy melt, which it is. You can see it has quite a bit of expansion in it in that all of these craze lines are occurring. And you can see that lithium carbonate itself is a really, really active flux. So it melts quite well at these temperatures. Okay, here we go. Sodium. Again, it's very, very similar to potassium. This is a really common flux. It's the strongest flux across all temperature ranges. It says from 900 to 1300 Celsius. Basically, you're looking at like 15 or 1600 Fahrenheit to 2300 to 2400 Fahrenheit. Okay. Produces really bright and brilliant glaze surfaces, gives really strong color responses. High soda glazes can often be soluble, which can be an issue. So for example, if you're using soda ash, which is sodium carbonate, it forms a bond with water and gets pulled out of the glaze mixture. So that can be a problem if you take away any of the water. You're literally taking the sodium out as well and changing the chemical formulation of your entire glaze. It won't melt as much. So people usually stay away from sodium soda ash or salt unless it's going directly into the kiln. Usually you want to use a stable source of sodium from like a feldspar. That's typically like NephSci or nepheline cyanide or Minspar 200 or some sort of frit. Okay, yeah, and you can see right here, this is soda ash, the top right here. You can see how active of a flux that is when it's just straight up soda. And then how this is nephcyanite, it definitely represents more of what you would consider a glaze surface. And because it has calcium, traces of magnesium, and then the silica alumina ratio is pretty low, and so far it's going to be a little bit more refractory in its melt by just itself, as you can see right here. But you can see the amount of sodium in the unity formula right here. It's 0.71. That's a lot of sodium. So NephSci we typically use in glaze materials, as you can see right here. And pretty high percentages. You could probably find a NephSci glaze ranging, an inclusion of of a sodium feldspar or a soda spar, anywhere between like 35 to 80%. This crackle snowflake right here is 90% NephSci. Which is obviously a lot of sodium, and you can see that in the relationship of the crazing and these kind of craze patterns right here. It also has magnesium carbonate, which you'll learn in a little bit. That also forms cracks and creates also a crystalline structure as it cools, which gives it its opacity. The ball clay is there just to give it a little bit of stability, probably holds it up on the vertical surface of the pot. Considering it has a lot of NephSci in it like that, 90% at, I think this is cone 6, it could just run off the pot. So you're going to need something to help keep it up on the vertical surfaces. Down here, this seltzer base, which is this right here, you can see it's got about 50% sodium Soda Spar is probably like Minspar 200 or something. When recipes get into just a soda spar, it's kind of hard to determine what they mean. That's like open language for a sodium-based feldspar. But again, these sodium feldspars differ in their relationship to how much sodium is in it, how much silica is in it. So you basically have to kind of test. Usually, when a recipe says sodium feldspar, I'm going to go with Minspar 200. That's usually what it means. If a recipe says nefs, if you want to use nefsi, it usually says nefsi in it. So that's kind of like recipe jargon. You'll be able to get used to that as we move forward. You can also see it's got a lot more silica in it. It's got 3134, which is a calcium borate frit, so it's got some calcium and boron in there. Boron is a really good glass former at this temperature zone. It also has whiting, which you can see it's at 11%. That's an auxiliary flux. So you'll have the main fluxing material, which is the soda spar, and then we'll refer to auxiliary fluxes, which are these other materials like whiting that has calcium in it, that also add to the melting potential. It also adds a different characteristic. It adds hardness. It will reduce the amount of crazing in the glaze. And maybe in higher percentages, it might start adding to opacity, which you can see like in the flowering right here. So that's probably from the whiting and could be from the 3134, which is also a source of calcium. Okay, the alkali earth. Okay, these are going to be our magnesia, calcia, zinc. Actually, zinc's not in this. I apologize. Okay. Oh, right, barium. Okay. Barium is a great source, a great material to use. Unfortunately, it is poisonous. I don't use it anymore in my functional glazes. So if I was making a pot with if I was making a glaze that I wanted to use with a functional pot like a cup or a mug or something, I wouldn't use barium. It's debatable in that they say if the glaze is consistently smooth, it doesn't have craze marks in it, that it is a stable material. But I just don't take the risk. If it's introduced to an acid, like coffee or something, it could leach barium out of the glaze if the glaze surface has cracks. So I typically don't use it. However, for like sculpture or for non-functional wear, it is an excellent material for mid-range, especially to make satin matte glazes. It is the go-to material. It is amazing. You can make really buttery surfaces with barium. Typically, the source material is usually barium carbonate. That's usually the only one that I'll ever use. Okay, so here's an example of a barium matte glaze. Okay, and honestly, barium is really well known for barium blues. So you could Google barium blues and you get these really beautiful high saturation blue glazes. And I strongly urge you to check that out on your own. But you can see right here, this is a barium blue, mostly nefsi. And this refers to theoretical. That's kind of like glaze chemistry jargon. There are theoretical chemical analysis and then actual chemical analysis. And sometimes, depending on where you're mining something, it might be just a little bit different. But the way that people figure out glaze recipes, sometimes they'll just go with like a theoretical or like an average chemical analysis. So whenever you see that, you can say that there's a little bit of room for error in there in the 65%. So anyways, okay. You can see it's 65 nefsi, so the main flux is sodium, but then the addition of 30% barium, that is a lot. And so the barium is going to have a major contribution to the surface. As you can see right here, it's this really beautiful, consistent matte, satin matte surface. Then you can also see there's some silica in there, probably to add a little bit of hardness, reduce some of the crazing from the nefsai. And then also a bit of clay. That just kind of helps stabilize the glaze. All right. So that's a pretty interesting. So that is barium. Okay, calcium. Calcium oxide is a great flux. It's a lot of times it can be used as an auxiliary flux, as in second to something else. However, it can be used as a principal flux in medium to high temperature glazes. It usually hardens glazes, makes it more scratch resistant, makes it more acid resistant. And it's useful in creating surfaces that are more matte. So these alkali earths will crystallize during cooling and form these really consistent kind of matte to satin matte glazes. In our studio, you will find it in dolomite, in wollastonite. Wollastonite is basically a calcium feldspar, and then calcium carbonate, otherwise known as whiting. It's also in like some borates, like Laguna borate is a calcium borate, and I think it's Frit 3134 is a calcium borate for it. I gotta double check. Anyways, we can look at that a little bit closer one-on-one. Okay, these are some calcium-based materials. Up here, this is calcium carbonate or whiting, CaCO3 right here. You can see it's not as, it doesn't melt on its own very well up through cone 10, but with other materials, it melts really well. Whiting is used a lot. In fact, it's one of the principal materials that's used in ceramic glazes. Cornwall stone is down here. You'll see it has traces of potassium and magnesium, so it's obviously going to flux a little bit more at those temperatures, as you can see right here. Okay, this is an example of a calcium, more of a calcium-based glaze. You can see kind of the surface qualities that calcium presents to a glaze. You can see these like little crystalline formations here. This is classic calcia inclusion into a glaze, like this little kind of Cretaceous. Oh, yes, it's Cretaceous blue. These like Cretaceous surfaces, what a great name. Okay. And you can see its relationship. It's got clay. There's a lot of clay in this. So, more clay, it's going to be a little bit more matte, obviously. And then with the wollastonite, the Frit, both of these containing high sources of calcium, that's going to produce more of a matte finish. So, okay, very good. Then there's magnesium. You will find magnesium in dolomite and talc. Talc actually has calcium and magnesium in it. And then magnesium carbonate. Magnesium is known for its ability to create smooth matte surfaces in high temperature glazes, usually ranging from cone 6 to cone 10 or above. In high amounts, molecularly, so in the unity formula, it will cause crawling. It creates a lot of surface tension with the melted glaze, and so it will shrink a lot after it melts, which is why we use it in the crawl slip. Yay. These, again, are examples of magnesium-based materials. This is magnesium carb up top here, okay? And then talc down here at the bottom. You can see how magnesium carb melts a little bit more than talc does, okay? But again, with the inclusion of other feldspars and other materials, it will melt really smoothly. This is an example of a magnesium-based, heavily magnesium carbonate-based glaze. You can see it's a crawl glaze, and you can see over here it's got all of these separations. And that is because we're taking advantage of the expansion relationship, or the characteristic due to expansion and glaze tension that it employs on the surfaces of glazes. So you can see here, it's got a lot of clay. It's got a lot of magnesium carbonate. That is a lot. Anything over like 5% magnesium carbonate, you're probably going to see attributes of like cracking and crawling like this. Anything that's in 10 above, for sure. Okay. It also has a lot of talc, so again, there's even more magnesium and whiting, which would be auxiliary fluxing. And then spodumene is probably the main flux. Spodumene is going to be really active. Again, that's lithium at this cone 6 range, so that's going to give you more of a melted surface, along with the crawling effect. And then there's Zercopax here. I guess they have that in to make it really, really opaque. I would expect it to already be really opaque with all the calcium and magnesium in it, but maybe the spodumene melts it out a little bit. And so they add this 10% Zercopax as an opacifier to make it completely opaque. Okay. All right, strontium oxide, don't really use it a whole lot. You find it in frit. Strontium carbonate is its main source. It contains similar properties associated with lead, but at higher temperatures. It is not toxic like lead, so you could use it for really strong color responses. And it's saying it's a good substitute for calcium and barium. It is really expensive. Okay, so that's probably due to its manufacturing. You probably need a whole lot of material and a whole lot of refinement to get a small amount of strontium, then raising the price. So I mean, I'm not going to tell you not to use it, but you know, there's no real reason to in our application unless you need the specific attributes that strontium provides. Okay, that's all for the slideshow. I hope that was exciting for you. Yay. Look for the next one. We'll get into different metalloids and silica and alumina. See you next time.